right, let's go through the review sheet. We've covered a lot in waves and sound, and if you can do this review sheet, you'll do very well on your test. Now, you need to be able to define all of these words, and I've typed out a bunch of the definitions. All right. Define a wave. You remember a wave is a propagation of a disturbance. There's many other things you could put on here. I want you to go through your textbook and analyze these problems a little bit more. A pulse wave has a single wavefront. All right, so that's a pulse. There's only one. While a periodic wave is one that repeats. All right, so something like this. The medium is just the material that the wave is traveling through. Material means medium. Medium means material. And a mechanical wave requires a medium. Remember all your M's. Now, a longitudinal wave. On a longitudinal wave, the particle travels parallel to the wave. These are sound waves, are longitudinal waves. Slinky waves, when you push it back and forth and they vibrate back and forth, these are longitudinal waves. So pretty much, let's see, if the wave is moving this way and the particles are sitting there vibrating back and forth, that's a longitudinal wave. Where a transverse wave we usually represent with a sine wave. The particle is moving up and down while the velocity of the wave itself is to the side. So for these, it's perpendicular, while for longitudinal, it's parallel. Okay, the crest is the highest point of the wave. So if this is my wave, the crest is a point. It's that point right there. While the trough is the lowest point, you can also say it's where the disturbance is greatest. But my trough is at the very bottom. While the amplitude is a distance from the equinodal line to a crest or a trough. Now the trick here, folks, is the amplitude is only half of the height. Do not give me the total height. That is not the amplitude. It only goes from the equilibrium line or equinodal line to a crest or down to a trough. The number of wavelengths that pass a point in a certain time, well, that's the frequency. And it's represented with F, and we measure it in hertz. While the time it takes one wavelength to occur is a period. And we use that as a capital T, and we measure the period in seconds. Sketch and label all parts of a longitudinal and transverse wave. All right. For a transverse wave, remember it's going to look like this sine wave. And here I'm going to give my equinodal line right here. So this is my equilibrium line. Amplitude is from equilibrium line or equinodal line to a crest. The crest is this point right here, and the trough is this point down here. And one wavelength goes from crest to crest or trough to trough. Be able to do this for your test. It looks a little bit different on a longitudinal wave. A compression is where they're squished together, where a rarefaction is where they're spread apart. Now, one wavelength is from here to here. Now, I can't show you an equinodal line or an amplitude on these, so don't worry about that. You do need to be able to put compressions and rarefactions to a sinusoidal line. Remember, your compressions always go to crests. So compressions always go to crests, while the center of your rarefaction always goes to a trough. So basically what I do is I go in and I put in the crests and the troughs, and then I just kind of connect the dots with as smooth a line as I can. It's kind of cheating that I've already got this here. You'll do a much better job on the test. Now, let's see. Blank interference is the overlapping of two or more waves. Well, interference is the overlapping of two or more waves. And when they interfere to form larger waves, that's constructive interference. When you get a smaller wave, that's destructive. It could also be partial destructive interference. Some instruments play waves that produce sound waves. I don't know. Here's my list. You come up with a list. If a cannon goes off in space, is it quieter or louder than on Earth's surface? Well, in air, there's no air. In outer space, there is no atmosphere, which means there are no particles. CLES, so there is no sound. Reflection is what happens when you have a wave, it goes down and hits a boundary. All right, the reflected wave at a free boundary it's identical and on the same side. That's what's actually more important. Okay, where at a fixed boundary, it's on the opposite side. That's probably a better way to word this. I'll fix this for next year. All sounds are created by a vibrating object. If you have a string wave, your hand is a vibrating object. Electromagnetic waves, vibrating electrons. Water waves, I don't know. What? Bobber all waves are created by a vibrating object. Okay, sound waves are mechanical because they have to have a medium. Now you need to know these. We can hear between 20 and 20,000 hertz. Anything below 20 hertz is infrasonic. Okay, this is what elephants hear. While anything above 20,000 is ultrasonic. This is how we see babies, and this is used extensively in medical technology. Now, sound travels faster through a solid, slower through a liquid, and then slowest through a gas. It doesn't travel at all through a vacuum. When sound waves interact constructively, they get louder. Think about it. Makes the wave higher, increases the energy. When they interact destructively, it gets softer. Now, wavelength is inversely proportional to frequency. V equals F lambda. The speed does not change. It depends only on the medium. So if the wavelength increases, the frequency has to decrease. That's what inversely means. Now, generally, when the temperature of a medium increases, then the speed of sound increases as well. So remember, speed of sound in air is 331 plus 0.6 T. So as the temperature increases, the speed increases. Now, what do we call the phenomenon when the pitch of a sound from a sound producer moving toward the object gets higher and the pitch of the sound gets lower when they're moving away? That's a Doppler effect. Now, relative intensity is measured in decibels, while threshold of hearing is what you can just barely hear, while the threshold of pain is the level that causes injury. What part of the ear is circular and resonates at different frequencies? We can use the eardrum. You can use the ear canal. I can see an argument for both. I'm not going to be that picky. The eardrum acts more like a tympanic. It's a tympanic membrane, much like a timpani drum. However, the ear canal does set up the resonant frequencies, so I'll take either one. Okay, when the intensity of sound is multiplied by 10, when the intensity of sound is multiplied by 10, now intensity is I, this is one that goes up by powers of 10, the decibels increase by 10. This is, you just add 10. And increasing 10 decibels makes the sound twice as loud. Go back to that chart I went through. Now, a guitar string produces a forced vibration, or you could call it a resonance in the body of a guitar, which amplifies the sound. When you get resonance, you get the really nice tones. When an object is vibrating at its own natural frequency without being touched, it's resonating. Now, A standing wave is produced when two waves of the same frequency and wavelength are traveling in opposite direction. They get alternating periods of destructive and constructive interference. The destructive occurs at the node, the constructive occurs in an antinode. Now, the first harmonic consists of two nodes and an antinode. What does that look like? Two nodes and an antinode. All right, this is my string. It is also referred to as the fundamental. So we're going to use those terms interchangeably. Now, the frequency of a harmonic on a string or open-ended pipe is determined by using the equation. Well, Fn is Nv over 2L. Remember, if you've got, let's see, let's do this. This is a string wave. You count the number of antinodes, 1, 2, 3. You can do it this way. So here my length is always going to be N L divided by 2. N lambda. Sorry about that. All right. And you can use all of the harmonics, even and odd. Where if you have a closed tube or a pipe, Fn is Nv over 4L, and you can use only odd harmonics for closed pipes. All for an open pipe or string. Now a node is an area of destructive interference, and an antinode is where you have constructive interference. Now beats are heard when you have two sounds of slightly different frequencies being played at the same time in close proximity. The number of beats you hear is the difference of the frequencies. Because remember, F beats is F larger minus F smaller, and F beats is always positive. Now, earthquakes can produce three types of waves. One of these is a transverse wave called an S wave. A typical S wave travels at a speed of 5,000 meters per second, and it has a wavelength lambda of 417 meters. What's the frequency? All right, we want to use the wave equations, V is F lambda. So now I need to solve this for the frequency. I want the frequency, so I have to divide both sides through by lambda. So the frequency is V divided by lambda. All right, so the frequency is the velocity, which is 5,000 meters per second, divided by a wavelength of 417 meters. So what kind of frequency do we get here? 5,000 divided by 417 gives me really close to 12. I'm getting 11.99 hertz. You can call that 12 hertz. I don't care. Okay, a wave has a frequency of 50 hertz and a wavelength of 6 meters. What's the velocity? F is 50 hertz. Wavelength is 6 meters. I'm looking for V. V is F lambda. So frequency of 50 hertz times a wavelength of 6. 50 times 6 is 300 meters per second. Using the wave equation is very straightforward. A wave is moving toward shore with a velocity of 5 meters per second. If it has a frequency of 2.5 hertz, what's its wavelength? Well, V is 5 meters per second. F is 2.5 hertz. I'm looking for the wavelength. So V is F lambda. I want the wavelength, so I have to divide both sides through by frequency. So the wavelength is V over F. V is 5 divided by 2.5. 5 divided by 2.5 is 2 meters. Okay, a hiker shouts toward a vertical cliff that is 826 meters away. Okay, now remember, this is the width, Okay, so if the width is 826 meters, and then you hear at a total time is 4.84 seconds. What's the speed of sound in air? So the velocity is distance over time. Now, what distance does it travel? It travels twice the width, okay, because it's got to go down and come back. So it's 2 times 826 divided by 4.84. So go on and multiply this across. 2 times 826 is 1652 divided by 4.84. And now do the division. And this is 341.32 meters per second. What is wavelength and period of this wave if the frequency is, okay, so if the frequency is 456 hertz, okay, finding the period is really easy. It's just 1 over the frequency. So it's 1 over 456. So 1 over 456 is 0.022. 219 seconds. And what's the wavelength? V is F lambda. I'm looking for the wavelength, so I need to divide both sides through by F. So I get the wavelength is the velocity divided by the frequency. The velocity is 341.32 divided by the frequency is 456. So 341.32 divided by 456 is, I'm getting 0.749, let's call it 0.75 meters. If the air temperature is 20 Celsius, what are the 3 shortest open-end tube lengths that will resonate with a 400 hertz tuning fork? And this is open. And what are the 3 shortest that will resonate? All right. So the first thing we have to do is find the speed of sound. So V is 331 plus 0.6 T. So it's 331 plus 0.6 times 20. All right, 0.6 times 20 is 12. So this is 331 plus 12. 12 plus 331 is 343 meters per second. All right, so Fn is NV over 2L. So now I need to solve this for L. So to do that, I'm going to multiply through by 2L. So let's see, I have 2L Fn is NV. Let's see. So I'm looking for L, right? So I have to divide through by 2 Fn. So let's see, that cancels. L is NV over 2 Fn. Now, it's open, so if n equals 1, L is 1 times, let's see, V is 343 divided by 2. Now, the frequency we have is, we have 1 tuning fork, so it's 400. So, this is going to be 343 divided by 800. 343 divided by 800 is 0.42, 0.429. Okay, so that's for n equal 1. For n equal 2, L is 2 times 343 divided by 2 times 400. So 2 times 343 is 686 divided by 800 is 0.875. 0.8 for space. I'm just going to do 86 meters. For n equals 3, L is 3 times 343. I'm going to go and just put 800 here because I've done it several times. 3 times 343 divided by 800 is 1.286. Let's call that 9 meters. Now what if you have a closed tube? For a closed tube, you have the same situation, only Fn is NV over 4L. So I'm going to solve this for L. Multiply through by 4L from both sides. So 4L Fn is NV. I'm still looking for L, so I'm going to divide both sides through by 4Fn. So L is NV over 4Fn. Now the only frequency we have that we can deal with is the 400 hertz. So for n equals 1, L is 1, V is 343, divided by 4 times, what was my frequency again, 400? So it's 343 divided by 1600. So what is that? 343 divided by 1600 is 0.214 meters. Now, for n equals 3, L is 3 times 343 divided by 4 times 400. 3 times 343 is 1029. Okay, 4 times 400 is 1600. All right. 1029 divided by 1600 is 0.643 meters. For n equal 5, L is 5 times 343 divided by 4 times 400. Getting carried away there. 5 times 343 is 1715 divided by 1600. Okay, and 1715 divided by 1600 is 1.071 2 meters. So 1, 5, 3, 1. You dip your finger in a pan of water twice a second. So the number of times you do it is twice, and the total time each second is 1 second. Producing waves with troughs that are separated. So troughs separated, that tells me that's my wavelength. Calculate the period, frequency, wavelength, and speed. All right. The frequency is the number of cycles divided by the total time. So the number of cycles is 2 divided by 1. So this is 2 hertz. Did I do that one backwards? Twice each second. Yep, so these are backwards. All right. The period is the total time divided by the number of cycles. The total time is 1 second. The total number of frequencies is 2, so this is 0.5 seconds. The wavelength is 0.15 meters, I read that. V is F lambda. So the frequency is 2 hertz times the wavelength, which is 0.15. So this is wrong as well. Imagine that. 2 times 0.15 is 0.3. Teachers make mistakes all the time. How long should a string be in order to produce a standing wave with 9 antinodes? So N is 9. And the string has a frequency of 180 hertz. If the tension is suggested, so the speed is 34 meters per second. Well, I know Fn is N lambda over, let's try that again. Fn is NV over 2L. So we're looking for L. So the first thing I need to do is get rid of my denominator. So I'm going to multiply both sides through by 2L. 2L Fn is NV. Now in this case, we can't just get rid of the N. We're looking for L. So we're going to divide both sides through by 2Fn. So I'm looking for L, so I've got to get rid of the 2 and the Fn. So L is NV over 2Fn. All right. So the length is N, which is 9. Speed is 34 meters per second. Divided by 2, and the frequency is 180 hertz. So multiply your numerator. 9 times 34 is 306. 2 times 180 is 360. 306 divided by 360 is 0.85. That's pretty close. All right, let's change that to a 5. All right, a piano tuner using a frequency of 392 hertz to tune a wire for a G natural hears 4 beats per second. So F beats is 4 hertz. What are the two possible frequencies? All right, F beats is F larger minus F smaller. Let me solve this for F larger. Okay, so if I add Fs to both sides, F larger is F beats plus F smaller. So if this is the smaller, then this is 4 plus 392, or 396 hertz. Let's solve this for F smaller. Now I'm going to do this a little differently than I did before. I'm going to add F smaller to both sides and subtract F beats from both sides. So that's going to cancel. So I have F smaller is, that goes away, F larger minus F beats. So in this case, if the 392 is the larger, and then the F beats is 4, all right, 392 minus 4 gives you 388.